Welcome back to Physics 246 Online. In this video, I'll give a brief introduction to the first two topics from Chapter 2 in Bevington and Robinson's book, the binomial distribution and the Poisson distribution. So at the very beginning of Chapter 2, we ask the question, what if we know that in a single trial of an experiment, the probability for success is p, and the probability for failure is then q, or 1 minus p? And if we do that single trial over and over again, n times, what would be the probability of getting a certain number of successes, x, out of those n trials, assuming that these are identical trials? That's what we're trying to figure out. So the answer is given by this quantity that's called the binomial probability. And there's a special notation that's used here. It's not too surprising that we might have this term p to the x times q to the n minus x, because if we do n trials and we get x successes, each of those successes had a probability p, and each of the failures had a probability q. So that makes sense. But what's this first term? Well, this first term is something that's called a combination. And sometimes people refer to this for shorthand as saying n choose x, and we'll see why that is in just a second. It's given by this term in the circle with factorial notation. If you haven't used factorial notation before, n factorial simply means n times n minus 1 times n minus 2 all the way down to 1. And so that's a shorthand for a product of quite a few terms. Notice that we can rewrite p to the x, q to the n minus x by replacing q with 1 minus p. So let's talk about the term in the circle. That is the number of combinations or the number of distinct ways that you can get x successes out of n trials. Because imagine, just for example, that we did 10 trials and got 1 success. Well, that 1 success could have been on the first trial, or the second, or the third, or the fourth, and so on. So there would be 10 different ways of getting that 1 success. And you'll see, if we take this expression here and plug in n equals 10, this would be 10 factorial over 9 factorial times 1 factorial. And that would give us just 10, as we already indicated. So p sub m, the notation here, is another way of writing down what's called a permutation. The number of permutations of x successes out of n trials. And then the x factorial that's in the denominator is what's called the degeneracy factor, because the number of permutations takes order into account. And if we don't care about order, we only care about how many of a particular kind of success that we got in our n trials, then the number of permutations would be divided by this x factorial factor. And so that's what gives us this term. And it's important that we take that into account when we calculate the probability of getting a particular kind of result. So each combination has this probability, as we already mentioned, so that the total binomial probability is the product of the number of combinations times the probability for each combination. So let's do an example just to make this a little more concrete. Suppose we toss 10 coins into the air. What's the probability that 4 will land heads up? And again, we don't really care whether it's the first 4 coins or the last 4 coins, or any particular arrangement of 4 coins, as long as we have 4 heads and 6 tails. So the binomial probability would be given by, of course, each head has a probability of 1/2, so there's 4 heads. Each tail, of course, has a probability then of 1 minus 1/2, or still 1/2, to the 6th power, because there are 6 tails. And then we take our number of trials, which is the number of coins, factorial, over 4 factorial, 6 factorial, and this gives us approximately 21%. So we would expect 21% of the time that we would get 4 heads if we toss 10 coins. A couple of things about the binomial probability function. This probability function, which is often written as follows because it's a function of x, the number of successes, but also the number of trials and the probability for success in each trial. It's a discrete function of x, where x has a range of values that go all the way from 0 to n. X, of course, has to be an integer because you can't have half of a success. You either get a success or a failure. And it has to be true that if we add up all the possible probabilities of all the possible number of successes that we get 1. In this way, the binomial probability is a normalized probability distribution. The central measures, we've talked about central measures being the mean and the variance for a particular kind of experiment or measurement. And so we can actually calculate those by using the definitions of the central measures. So if mu is the expected value of x, the average value of x, we would take x times the probability function, sum this up over all of the possible outcomes from 0 successes all the way up to n successes, and you will show for homework by using just a very clever substitution, variable substitution, that this can be written simply as the number of trials times the probability for success in each trial. And that actually is pretty intuitive if you think about it, because if you had 10 trials and the probability for success in each trial was 1/2, then we would expect on average 5 successes. However, the variance is a little bit more complicated, and through a similar kind of variable substitution, we obtain this answer here, which is np times 1 minus p. Notice, though, both of these forms are quite simple. Now, a couple of comments before we move on to the next probability distribution. The binomial distribution function, although it's very useful for things like flipping coins or rolling die, it's of pretty limited use in most of experimental physics because it's defined in terms of the probability for success in any given trial. And we don't usually know what p is in most experiments that we do. Also, it applies only to discrete values of x, does not accommodate negative values of x, and it can be only calculated for small values of x, because if you go back and look at the form of the binomial distribution function, you'll see that you've got these factorial terms, and it's pretty difficult to calculate factorials when you have numbers that are large. So there are special cases for which the binomial distribution is helpful, but it's usually just a starting point for the next distribution function that we're going to talk about, which is the Poisson distribution. So let me go ahead and introduce that, also from Chapter 2 in Bevington. And there's a reason why we start with the binomial distribution and then go on to the Poisson distribution, because they are closely related. Now, suppose we don't know p for the probability for success in a single trial, but we do know that it's really small. And we're thinking now of counting experiments where the success might be the decay of a radioactive nucleus. And we're waiting for a certain amount of time to see if that decay happens. And that represents a single trial. But if we make that time interval small enough, we know that the probability that this happens would be very small. So the question is there a convenient way of estimating the probability that we get x successes out of n trials, where n is very large and, of course, p is very small? The answer is yes, of course. And so the Poisson probability is the limit of the binomial probability in this limit where p goes to 0, where p becomes very small, and of course we've already mentioned that n has to be very large as well at the same time. So we can take our binomial distribution function, apply this limiting case, and in just a few slides we'll be able to show where we end up is this very simple functional form here. Notice that this result for the Poisson distribution function does not depend on the probability for success in a single trial. And that's what makes it useful to us. All right, where does it come from? We'll start with the binomial probability in the same form that we showed on in our previous set of slides, where we have the term here, the first term out in front is the number of combinations, ways of getting x successes out of n trials. And then p is the probability for success in a single trial. 1 minus p is the probability for failure in a single trial, and then we have, oh, I see, right. So the this it took me just a second. The product of these last two terms would be 1 minus p to the n minus x, right? And that is exactly what we had. If you go back and look at the binomial distribution function, this simply separates that one term out into two terms. So we're going to take 1 minus p to the nth multiplied by 1 minus p to the minus x. But it's the same thing that we started with before. So we're going to examine each of these factors in the limiting case where p goes to 0 and n is large. So the 1 over x factorial, we'll leave that one there because that actually appears in the final form for the Poisson distribution function. So what about n factorial over n minus x? We want to examine this and find the approximation that holds true where x is small. So if we look at the meaning of the ratio of these two factorials, what's going to happen is the numerator will give us n times n minus 1 times n minus 2 and so on. Eventually, when we get to n minus x, all of the terms n minus x and smaller will cancel out with what's in the denominator. So we'll simply be left with n times n minus 1 times n minus 2 all the way down to the term that's just one larger than this term in the denominator. Okay, so that's a rigorous result. We're not making any approximations yet. Now let's look at the product of all these terms. You can show by inspection that there are x of these terms here. And if x is small compared to n, then each of these terms is essentially the same size as n. And so to a good approximation, this is simply n times n times n x times, or n to the x power. So the limiting case for this ratio, where p goes to 0, in other words, where x is small compared to n, is we get n to the x power. All right. So now what that does, if we combine that with the p to the x term, we put them together and we get n to the x times p to the x, which is np to the x power. We already know for the binomial distribution function that n times p is the mean, and so we replace that with mu to the x. So that has already simplified tremendously. So now this approximation for the binomial probability is given like this. So all we have to do is simplify these last two terms in the approximate limit where p is small and see what we get. So let's look at the first one. 1 minus p to the minus x. Well, if we know p is small, then we can write this in a Taylor series expansion. And we can probably just keep a few terms. And it turns out, actually, in the limiting case where p goes to 0, then this just becomes 1. And it's a good approximation to just let that term equal to 1. So you might think that we could make that same argument for the last term, for 1 minus p to the nth power, right? If p becomes small, isn't this also just 1? And it turns out that's not a good approximation here because n is very large. And so it would be oversimplifying to set this last term equal to 1. It is going to be small, but it's not equal to 1. So what we have to do with the last term, okay, we've already got the binomial probability simplified down to 1 over x factorial, mu to the x, times this 1 minus p to the nth power. What do we do with this? Well, we know that mu is equal to n times p, right? So n is mu divided by p. And if we write it in this form here, and we're going to take the limit of this quantity in the brackets raised to the mu power, where p goes to 0, you might remember having seen that there is an expression that's equal to e to the x power. And e to the x is the limit of 1 plus x over n to the nth power, where n goes to infinity. And so where n goes to infinity, since mu is equal to n times p, and mu is a finite value, where n goes to infinity, that's the same as p going to 0. So all we have to do to use this expression that evaluates e to the x is let x equal to minus 1 and let n be 1 over p. And if we plug both of those into this expression here, it gives us back exactly what we have over here that we're trying to evaluate. So what this becomes, if x is equal to minus 1, right, then we get e to the minus 1. So this limit of 1 minus p to the 1 over p becomes e to the minus 1. That gets raised to the mu power, and that becomes e to the minus mu. So you can take a look at that and satisfy yourself that indeed this is correct. So the result that we get, which is, remember, the limiting case for the binomial probability when the probability for success in any given trial is very small. It started off rigorously with this form, and we have found that in this limiting case, we get simply 1 over x factorial mu to the x e to the minus mu. This very, very simple form that only depends on the mean value and on the number of successes. And so we'll just close with a couple of comments and observations about this function and how it differs from the binomial function. It applies, just like the binomial function, only to positive and discrete values of x, because if we're doing a counting experiment, you can't, in a particular interval of time, you can get 1 event, or you can get 2 events, or you can get 3 events, but you can't get 2.5 events. So we're counting things that are discrete integer values. It applies for cases where the probability for success in any individual trial is very small, but n is very large. And so this could be a counting experiment where the counting interval is only 10 seconds, but we count for 5 hours. So the number of individual trials that we're doing is very, very large. And of course, that means that the number of successes in any individual trial would be expected to be small. And the nice thing about it is we can evaluate it easily. It only depends on knowing x and mu. We don't have to know the individual probability. One more thing, it's also we've said it's a discrete function where x has a range of values that can go from 0 to n. And if we use the functional form for the Poisson distribution and sum up all of the possible outcomes for 0 successes all the way to n successes in our n trials, you can show that you can take the expression for the Poisson distribution, pull outside the sum e to the minus mu, and what's left as the sum is the Taylor series expansion for e to the plus mu. And so indeed we get 1, which confirms that the Poisson function, the Poisson distribution, is a normalized probability distribution. We once again would like to determine central measures, so we'd like to know the mean and we'd like to know the variance. So the mean is really, really easy to evaluate because we start with this expression here, right? We take the x multiplied by the probability of getting x and then add that up over all of the possible outcomes. And we find out that you can pull outside this term, you can pull out a factor of mu, which leaves behind mu to the x minus 1, and you can pull out a factor of e to the minus mu, because that doesn't depend on anything, any value of x. So those two come outside the sum, leaving behind this term. And if we just do a simple variable substitution, a nice trick that you'll use on one of the homework problems, let's just let x minus 1 be another variable y. And so then what happens is this summation becomes the sum from y equals 0 to infinity of 1 over y factorial times mu to the y. And this again, like we said on the previous slide, is the Taylor series expansion for e to the mu power. So we get mu, e to the minus mu, the summation gives us e to the plus mu, which gives us mu, right? So we knew that that had to be true, but this confirms it, this verifies it, which is nice to know. And the variance can be calculated as well. It's a little bit more complicated to do. It's the same basic procedure using the same kind of variable substitution, and I've assigned this for you to do for homework. But the really nice thing about it, and maybe a little bit counterintuitive, is that the variance turns out to simply be the same as the mean. And that's something we wouldn't necessarily have guessed, but it is true. So the variance is mu, which means the error, the standard deviation, is the square root of mu. So knowing the mean gives us, of course, the mean value and then also the variance of the distribution. So final comments, Poisson distribution applies where the values of x are discrete, counting experiments like I've been saying, the number of successes has to be greater than 0. You can't have a negative number of events, and x has to be small. So the way we achieve that in practice is by making our individual trials short trials for counting experiments. We can satisfy that requirement. So I hope this has been a useful introduction to these two distributions. You can see they're related to one another. The Poisson distribution is the one that has greater applications in experimental physics. So I will see you in class.